So, welcome. Fifth lecture. Due to the nature of how this course is arranged, this is the midway point for the theory lectures. There's 5 left after this one. And I'd actually want to start with an announcement this lecture. I have just on Friday had a talk with an industry person who is willing to give a talk about software development and maintenance practices on this year's visiting lecture. So we, at least for now, it looks like that we will have a visiting lecturer at the latter part of the course. So, and when we set the date and the exact topic and what he's going to be talking about, it's going to be announced on the Moodle website. Right now I can tell you that it's a large multinational software company focusing on Finland, on government contracts and these huge software systems, which more or less, once they are deployed, are in market for 10 years, something like that. So definitely all the things mentioned on this course, all the things we discuss on these lectures are going to be somehow presented on their way of working. So, but anyway, on this fifth lecture, like always, we'll start with a quick recap, especially since I was traveling last week and unfortunately arrived to Lappeenranta on the afternoon last Monday. So last week we were talking about regression testing and live development. Basically, we all know that every time we put something online, it's probable that someone is going to find an error from our work. Of course, this means also that the changes or the maintenance cycles of software can also be faulty. In fact, depending on the type of project and the industry area, from 2 to 20% of injections, meaning that something is changed on a live system, is somehow faulty or bad and not necessarily breaking things down, meaning that the system still functions, but for example, bad fix makes the performance worse, or something which is technically broken gets fixed, but unfortunately it also affects the way the system works. Sometimes there's even broken patches. It's not completely unusual. And this of course means that you have to roll back about every 20th to 5th update or daily update. This is of course no problem if you are running something like a continuous delivery, where the exact idea is that you can control which versions you put online, and sometimes even might do little experimentation like deploying different versions of your system to different countries, or guiding your traffic, let's say 10% of the users to version A and rest to the version B, and see if the A version is considered generally preferable, or it's prototype testing some existing technologies. For example, Amazon does this to you. You won't notice it, but usually Amazon and other large companies are running a bit different layout versions on some regional markets before they decide on what changes are introduced to the main version, which is the default for everyone. But anyway, to ensure that we get the bad fixes caught easily or quickly, we need to do regression testing. Basically, the name means that we just check that we are not introducing new faults or breaking anything that was once already fixed. And of course, this leads to the live development. The idea that you can keep the system online and still make new changes, additions, and the customers, because they are using your software or product as a service, or even if it's a completely independent mobile application, it receives patches from time to time, isn't exactly a new idea. It's, in fact, most of these ideas are way older than mobile industry, for example, or the high-speed, omnipresent internet we have today. Of course, today, if we were talking about delivering software in any other way than providing a link or thin client to one end, the customer, and then setting our system on a server or something like that. If we are not doing that, some people might consider us a bit crazy for going that way. But interestingly, this extreme programming with continuous integration and continuous deployment, they are from the early 2000s. Continuous integration is actually a 20-year-old idea at this point, even though the systems or the technical infrastructure which allows this to happen in daily life without being a huge international company with resources and money to do this sort of thing, like, for example, SAP systems, which have been used on international scale resource management and the systems forever. But we can now do these things and do them on quite easily, even without having a huge multi-billion-dollar business. The current ideas, the continuous deployment, continuous delivery, mean that we always have version available for the users. We always keep functioning version as the one we put our customers in, but we can also test out new ideas. We roll back to the previous version if we had a faulty things. And actually this experiment system, which more or less doesn't have a name yet, is the approach where we are doing even some end stage acceptance testing or usability testing while we are already putting the system online, because we have a good degree of separation between the functional logic, the databases, for example, the account management and order management, and the user interface is just a layer which sits nicely on top of everything. More or less, this is the idea of the model view controller architecture or breakdown, where we have the data objects, activity objects, and the views which combine these things into something functional, defined separately. But the idea is a bit more complicated here. It means that the entire system is built so that every time we do some changes, do some additions, fix some bugs, we run automated regression tests, and if everything works, we put it online. That's more or less the idea of it. Anyway, this wouldn't be a very interesting lecture or interesting thing really to talk about if we didn't have problems with it, obviously. Of course, if we are doing daily builds or daily deliveries or daily updates or even weekly updates, it means that the time schedule is quite restrictive. Of course, we can't expect the team to do any huge changes during 1 week or 1 day or 1 cycle of development. And on most occasions, if we start to look into why design fails, why actions fail, why we have bad patches, bad fixes, faulty additions to our currently functioning systems, it's rather easy to find out that these things are connected. Usually, it's not just that the people aren't experienced enough. It's usually not that the design is a bake and doesn't actually understand or get the idea why our customers want to do things. It's not only that we have a bad or spotty testing or quality assurance practices, or that our integration activities overlook certain things. It's more or less always a combination of all things. But of course, on this example, on the slide, it says that the testing is the capstone in this organization. Considering that this map of connected problems was made from a real problem solving or quality assurance or quality control workshop day on a real organization, it could indicate that this organization, for example, needs to consider how it does software testing work or quality assurance work, because that's more or less the place where the things are bad. On the other hand, the product design is causing most of the testing issues, and the integration itself seems to be a bit difficult. But nevertheless, there are always several connected problems, unless it's a very peculiar situation. Which brings us to today's lecture. So, code smell, refactoring, and technical debt. These are things that you probably have never heard about if you are just doing the first iteration development, because these are more or less things that are heavily influencing the way and need of software maintenance work. So when we do the first iteration of the project, when we put it first online for the first customers to use, we have had it in acceptance testing, or in general it has been developed over a couple of months, perhaps a couple of years, and we more or less have a system which functions well enough that we want to put it out, or we have to put it out for financial reasons, whatever they may be. But anyway, these three things more or less are symptoms of work being done on the cheap, or cutting corners, or trying to improve the existing system. Meaning that these all three things are mostly stuff you heard about on the software maintenance course, in comparison to some other things which are more or less about the first software design. So, like mentioned earlier, these are more or less the indicators that the system has some decay in it. Now, this slide is almost in every lecture, because these are more or less the indicators or things that you probably want to look out for when you are thinking about what are the things that affect our software or product, or why it's functioning badly, what could be done, what are the areas of improvement we could pursue. Basically, if we have time, there's a possibility that we can do technical improvement maintenance. But of course, this is on the preventive maintenance cycle, which is only 4% of the time. But on the other hand, when we are releasing a new product, for example, making a new version of software or adapting it for some other use, there's usually talk or possibility to do some refactoring or recreate or rewrite the existing modules so that they function a bit better than earlier, or remove the unnecessary clutter and stuff like that. But anyway, if we do preventative maintenance or just want to use our resources and time on enhancing the product, we have three concepts: code smell, code refactoring, and technical depth, which are all something that could not only explain why system decay happens, but also gives you an ideas and ways, tools to identify which are the most probable problematic areas of your software or source code repository. So if you need to select something, you can look for certain symptoms which you could fix or try to alleviate. It's a bit similar like the concept of cyclomatic complexity. If the object is too complex, then it's probably better to recreate it or divide it to several other components, because maintaining it or fixing it or updating it becomes a nightmare. But anyway, let's start with the technical depth, because this is something that's more or less about the activities which actually start even when we do the first iteration of the software. The technical depth, in definition, is the costs which are caused by using shortcuts to develop the system. There's a couple of definitions. The first one here, the cost associated with a lesser software system that became difficult to maintain and improve. The debt within the system becomes a constant anchor on software productivity and impedes the ability to efficiently add new features. Delayed technical work that is incurred when technical shortcuts are taken, usually in a pursuit of calendar-driven software schedules. Just like financial debt, some technical debts can serve valuable business purposes, meaning more or less that when we need to do something within certain deadlines or with certain amount of money or time or whatever, we can't always make the best possible solution. We have to make the one that works and live with that. Of course, it leaves areas for improvement, and of course these things are considered technical debt. So basically, one thing to understand is that technical debt isn't a death sentence. It's not something that's telling you that your organization is a mess, your development processes are completely horrible, or so on and so on. In each project, you probably generate some debt. Not perhaps because it's needed, but more or less because the experience or capabilities of the time were limited in a sense that you just had to make a simpler version, or let's say lesser version of your system, so that it's actually ever delivered to customers. When you have time to start fixing the technical debts, then we are talking about ways of improving your software. Considering that, for example, the Amazon and Netflix both recreated their entire infrastructure or redefined the entire way their system works, was actually can also be considered somewhat technical debt, because the organizations didn't have time or resources to do all the development work and testing work and create a new approach on virtualization for the first version, simply because it would cost a comical amount of money. So in the later development cycles, the organizations decided to pay out the debt and create the back-end system in a way that actually supports their amount of customers and user spikes and so on and so on. But anyway, if we consider the technical debt, we basically have two axes of things. Is it recklessness or prudent work, or deliberate or inadvertent problems? So basically, if we are considering the reckless approach, which is perhaps the most difficult one or worst one, because it's more or less about the organizational culture, it basically means that we do not have time for design, or means that we do not have time or any interest in making the design works function well. We just make something that works and are done with it. Of course, that's a horrible business practice, but sometimes it's a reality. Also, if we aren't doing it deliberately, it might be something like what is layering. So we are doing something, or the project is doing something that's on the upper limits of the technical capabilities of that time. The organization might not have the necessary skills, or it might be so difficult problem for the organization to solve that they are just doing or using something that works. Perhaps in the later iterations, when you have enough experience or new tools or new modules or components which can make things easier for you, you might then recreate the technical solutions in a more sophisticated way. But still, recklessness, if it comes from the fact that you don't simply have the knowledge to do things, is not something that you can really blame on the people. Maybe the deliberate recklessness can be, but the inadvertent is something that's just going to have to be fixed later. Of course, if we take into the account that we don't necessarily want to be hostile or not consider it a bad thing. Sometimes we have to just ship it now and deal with consequences. Like I mentioned, if you are running a smaller organization and you have very limited resources, you will put out what you can, or that you have a customer who demands really strict deadlines, you probably just make something that fulfills the contract or allows the customers to do the functionality they want to have. We'll fix it later if it's worthwhile to fix. And finally, the last one, now we know how we should have done it. So sometimes you are the trailblazer of a software organization. You are doing something new, a bit experimental, and or there's new technology involved. So you can't know what the end result will be, but when you get something out, then you get also ideas, experiences, feedback, reports, or find in practice what parts of your technical solution isn't as robust as you would want to be, so that it works. And like mentioned, all these four things probably happen in one or several ways in all projects. Having some technical depth, meaning that you have to fix things or leave some problems or fundamental issues to be fixed later during the maintenance, is not a negative thing. It's a reality of life, and if you are doing a long maintenance of a product which is going to be on the market for, let's say, 5, 6, 10 years, then you probably are going to be doing some refactoring or fixing these technical issues anyway. So you might as well publish it when it works and then see where the technology takes you, because of course you have to remember that, like of the couple of lectures back, I mentioned that the user preferences change, the technical platforms change, everything you do in a software development work keeps changing a bit, so you will have problems regardless if you made a perfect solution or not. So that's why the perfect solution may not exist, or it would be unwise to spend money and time making the optimal solution and trying to eliminate every technical debt in your product before the first launch. It's called perfectionism, and it's usually not a very good thing. Of course, there's a couple of things, list of areas or concepts that are very symptomatic for your project having too many technical depths. There's too many, let's say, quick fixes or batch over batch over batch. It's a patchwork. Your software is a sort of a patchwork guild, which functions with exceptions to exceptions to exceptions, and it becomes a completely horrible nightmare to maintain and keep up. If you accumulate many of these hacked together fixes, you might see something like that the customers don't like your product, there's a poor responsiveness, there's long delivery times, you simply cannot fix things fast enough or change things fast enough, because if you change something, something else breaks down, and it takes a while to understand why these things happen. There's lots of defects because everything is held together with exceptions. If we make one change to the software, we might have unexpected problems later on everywhere else. And also this leads to the rising development costs, because of course you have to fix and refix everything to have the system hold together. And of course this usually leads to frustrated and poor development teams, because well, some people who consider themselves a sort of an artist in the software development work or software programming work might not like the idea that just hack together something as long as it works approach, or they understand that if it's done right, then everything would be so much easier, but there's no money or interest in doing that. And in general, every time you make or use these sort of approaches, the mounting problems makes the maintenance cycles more laborious, costly. It makes it more difficult to add new features, fix things that annoy your customers or users, and so on, which is also why in many occasions the software, in the software world, some products at the end of their life cycle are just abandoned and replaced with something that does the similar thing but works much more fluently. So in these cases, it can be said that the technical debt more or less kills the product because it wasn't managed and you weren't doing anything. So, of course, being a software engineering course and a software standardization course about how things are done, there's a couple of ways you can measure what happens or how much technical depth your system has. This list was collected from the one research into understanding technical depth. So what is it, how can it be observed, and what are the most important things which can tell you that, okay, we are having problems? These are more or less the things that you can use as a priority list of understanding how much patchwork or how much fixes your software should probably need. The first and most serious one is, of course, the amount of duplicate code. You all know that it's a sign of a very bad approach or very bad practice of development when you have duplicate code on your system, because it means that on some level someone has not been working with the someone has designed the system so that you have to have the same code or the same algorithm or same activities over and over again. Of course, meaning that if you need to make some changes, you have to find all those instances, and that would be a freaking nightmare if we are talking about the huge source code repository. So basically the duplicate code is something that's most common metric or most glaring metric of technical depth. Also, some things like rules compliance and comments are good measurements, because the rules compliance means that you have some design, you have some definition on how we, for example, comment our code, how we identify the people who are working on it, how do we implement certain things so that the source code retains its understandability. Because you are not writing the source code for yourself, you are writing it for the entire development team, and if you are just making small changes here and there, not following the rules your organization has set for making an understandable code, it usually means that something was done in a sort of a hacked together approach. Also, the amount of comments themselves, this is actually interesting because it's not that the comments themselves are bad, but it's actually interesting that in many occasions, the amount of extra commenting or extra comments or added explanations on how things work is actually a very good indication that here is probably something that's going to be broken or isn't implemented completely correctly, or that the developer or programmer who made that part of the system didn't actually understand entirely what the system was needed to do and had to make several notes for themselves, or had to use a solution which needed additional explanations on top of the things that we already do. This also, on the technical side, something like interdependent packages or class complexities are also showing that the technical depth is accumulating here. Like I mentioned earlier on the cyclomatic complexity, and there's the number of was it 11 anyway, that says that if the object or module is too complex, it needs to be revised or divided or something done to it so that it's easier to maintain, easier to fix, and easier to make changes. So of course, if we have high and huge complexity methods or classes, it more or less shows that this probably needs some refactoring work. Finally, also, the automated test coverage is, if the level is low, it usually means that you have to do a huge amount of manual testing work to ensure that all the different small changes, special cases, so on and so on work. And that's usually an indication that it will be a painful work to maintain the software. It's also going to be a mind-numbingly dull if you are doing the same manual test cases or special test cases manually week after week after week, simply because you don't have the possibility to automate things, or there are so many changes or so many interdependent activities that you have to check by hand that the automation doesn't miss anything crucial. So anyway, these are more or less indications that you have the ways to measure how much decay in your system there really are. So, of course, technical debt also causes is something that can be caused by the process. It's not always development practices. It's sometimes the design errors carried into the actual implementation. And for example, if we look into how the software process, testing work, design work, can affect these things, well, of course, if we have poor coding and testing practices, that's a gimme. If there's a system design which doesn't actually define things very well, or if we use more or less wrong or badly designed approach, then of course we will have to do huge amounts of maintenance work to fix all the problems that should have been already caught in the original design. Also, if we are talking about a large project, more than 20 people or even more than 10 people, it's important to have these communications and to pay attention that there is a communication and collaboration between the different development teams. There's a study saying that if we have any more than 7 people in our development team, we no longer have the capability of knowing who is doing what. And in fact, actually our own research into development practices say that largest and most important thing on quality assurance work is to have the capability of knowing who is the person who implemented the first design, or who is the person who have implemented the changes, so that when you are trying to trace down problems, you can ask from someone else who might have experience or understanding how the underlying system works. It's not really rocket science, but it's something that has been said here several times already, that if your, for example, quality assurance and development and designers don't communicate their problems, their ideas and their issues, then there's no way of knowing how it affects the process. If the designer thinks that the developer understands their ideas without actually telling it to them, it probably means that something's going to fail. Similarly, the software person doing the quality assurance work might be doing something with a module that they have never written. They have never developed a one line of code there, but they have to debug it because it's probably causing problems with something that they are working on. So of course, it's easy to understand why these might become a problem. Of course, there's some other things like lack of standard development process, meaning that no one actually really knows who is doing what and who is responsible for what and what should we do next. There's poor requirements, no definition of done, meaning that it's easy to get lost in the jungle of making small changes here and there, which obviously isn't very fruitful, and lots of manual effort and lack of proactive investments in paying down the debt, meaning that we decide that we are not going to be fix any of these structural issues or architecture issues. We just may keep the system alive. Okay, so of course, repayment plan is, well, it starts with, it gets a bit abstract here. Of course, if you are a software developer or project manager, you really can't do anything unless you get the upper management to allow you to use the development cycles or maintenance cycles on fixing certain issues. Of course, most sensible organizations do this because it's bad business to have a bad product. But on the other hand, it's also important that you understand what is the life cycle of the software you are working on. If it's end of the line product, which is on which your organization is just waiting that the last contracts go out and then you move to something else, it's obvious that they are not going to be investing money on repaying the technical debts and technical problems in it. But if they are still working with the product, doing business with it, it might be useful to start considering the refactoring work. Which brings us to the second part of the lecture. So consider that we have a product which has technical debt. It functions okay, there's enough users on it, it's a financially sensible product, but there's several problems in it that perhaps your organization wants to expand your product, release a newer version of it, or make some changes so that it has more features, so that it attracts more customers, or you are launching on a new market. And of course, this means that you might want to actually fix the issues of technical debt, and the code smells and refactoring is actually something that affects, that addresses these areas. First of all, it's important to understand that good developers do not write bad software or bad source code because they don't care. Like mentioned on this course several times already, the requirements change over time, and of course it means that you have to keep up with the changes, and it requires you to make, even in the best scenarios, some changes which might not be possible to do easily on that solution or that architecture or with that development engine. Also, time and money are things that most organizations might not have. And in general, what is the development of bad software? The question here, how do we know our software is bad when it works fine? Well, if it has technical debt, it's not the end of the world. If it's difficult to maintain, that's the level where we need to take into consideration that we might want to fix something. So this brings in the refactoring work. So basically, the refactoring work means that we modify the software to improve its readability, maintainability, and extensibility without changing what it actually does, or what it's actually doing. Meaning that we find parts which are too complex, which lose power, which are badly optimized, which somehow limit our system, and recreate them with the approach or with the solution that actually does exactly the same thing, but it does it better. So we do not add new functionalities. If we refactor our software module, the idea is that the interfaces and parts are still exactly the same that they were before refactoring work, but we just fix all the smaller problems within one module. meaning that this, in a similar way than, for example, if we are designing an engine, we would change out to better battery or better charger, or doing some small changes, ensuring that the engine runs smoother. The user, or the person driving the car, doesn't know anything, they just turn the key and drive away, but you've made a design change or refactored one module which makes everything work better. This might also not only better towards the customer, but for example, if you incorporate all the changes or small changes from the last year to the refactored module, it might mean that there's a fewer amount of exceptions and problems in your product, so it's easier to maintain. Everything is run through the same process, so it might mean that it's easier to test, it's easier to ensure that there's no problems, and it keeps the maintenance cycles short and cheap. So, of course, you are writing a code, so you might accidentally introduce new bugs to the refactored modules. But of course, this is expected. It's basically the development work in which you make a new subsystem or new sub-solution and switch out the old one, which might have some problems or might be unnecessarily complicated, or might just be useful if it's written according to your coding conventions, so that it's easier to follow how it works. Of course, if we talk to management and you tell the management that I want to use a software maintenance cycle, I want to spend time and money, not make any visible changes to the software, but perhaps might actually make it more prone to breaking down or break something. And we need to recalibrate or recreate our test automation suite. We need to redefine our test cases, and this all will not affect the end customer in any way. They will probably tell you to seek help and or go away. But in organizations which want to or try to ensure that the product is still something that's competitive or usable, this is something that still needs to be done. So we are doing refactoring work simply because it improves the technical quality of the product. So we don't necessarily need to refactor everything, or we just pick parts there and there so that we can keep the product maintainable. We keep it simple enough, or the source code simplistic enough, so that it's fairly straightforward to make changes. And actually, the Highsmith book, Jim Highsmith is one of the original Agile Manifesto signees who more or less were on the one of the researchers who defined what the Agile approach is, mentioned that this is something that's basically the most fundamental aspect of agility. This is also why refactoring is done in almost all software organizations which realistically develop anything, because this allows the organization to first put out something that works, and then we just refactor the module or refactor the component or the activity when it needs to be fixed, or we need to have it functioning more robustly so that it's easier to maintain. So basically, this is one definition. This is from testing extreme programming work. So duplication and needless complexity are removed from the code during each coding session, where even when this requires modifying components that are already complete. Automated tests are used to verify every change. So basically this is a bit older book, and this more or less defines what's the basic level of refactoring work. Remove unnecessary complexity, remove duplication, remove all the exceptions if necessary. Of course, sometimes you need to have them. Also, Kent Beck's definition. This Kent Beck is also one of the persons who was involved with the original Agile Manifesto, and Beck is also the person who is running the test-driven development process and was one of the original authors of the, I think, extreme programming, if I remember correctly. But anyway, a change to the system that leaves its behavior unchanged but enhances some non-functional quality: simplicity, flexibility, understandability, or performance. So some small modifications to enhance performance, some rewriting work for the source code simply to get fewer source code lines into the work, remove unnecessary options, for example, if it's a larger overhaul, or add flexibility, improve understandability, these sort of things. So development for the sake of the developers. And finally, yet another Agile Manifesto guy, a change made to the internal structure of software to make it easier to understand and cheaper to modify without changing its observable behavior. So all these definitions more or less come back to the same thing. So refactoring means that we make the source code more understandable. We don't want to make large changes to the behavior. In fact, the behavior stays exactly the same. But in more or less, we aim for enhanced software quality, simpler code, more flexible system, and get rid of the duplicate code and needless complexity. So, of course, I mentioned earlier that this idea is sometimes fairly difficult to sell as a software developer or software project manager, because it doesn't necessarily have any way of proving its worth to the management. But if we want to start considering what it does, first of all, it prevents the system decay, design decay. It finds bugs. It reduces debugging time. It also means that the system probably saves money in the long run, because you can do additional features, you can do changes according to your new customers, or you can react to the platform changes, and you don't end up with the high technical depth and all the system decay symptoms, which are usually listed on the first slides of these lectures. So, of course, there's some guidelines on when refactoring is done. This is something that's probably meant more towards the software developers. And first of all, do not refactor something that doesn't work. If your system doesn't pass all the tests, if your build is broken, of course, you do not want to do refactoring work there, because you first need to fix the problems. And when you try to find the area, the codes that smells, there's usually a couple of ways to find them. Of course, the code duplicity is one of the things, but there's also a huge book of design patterns, which are code smell design patterns, meaning that there's different behavioral aspects on what the object or the component is doing, and what is bad behavior or what is dubious behavior, which probably means that this part of the system could be improved. Of course, the code smells mean that there's part of the software that isn't working as it should be. I'll get back to that a bit later. There's a couple of examples of what code smell actually means. But anyway, first you ensure that all the tests pass, and if you don't have anything set to do, then just find a part that's bad or has the early symptoms. First decide how do you want to do the simplification, make the simplification, check out that your simplification did in fact work, and then you might want to do something else. Of course, like always, if you are making changes to live software, you might want to do this one system at a time, because introducing several new refactored components and having a explosion of problems means that you are, well, in deep water, because you can't know which of the changes actually broke the system. And that probably leads to a discussion with your project manager or someone who is the product owner. So basically, there's some things, requirements for refactoring work. Usually, the PECs list here mentions that there needs to be ways of testing the system. This goes back to the first lectures. You have to measure something, because if you don't measure, you don't understand, and you can't manage what you can measure. So of course it means that if you need to have a fairly robust test automation or test coverage to begin the refactoring work, simply because otherwise you will be spending your effort on making changes or fixes or additions which might not actually be useful. Of course, if you don't have the tests or you don't have the test coverage, it means that your next maintenance cycle should be improving your test coverage, because you need to have some way of proving yourself or proving for quality purposes that your refactoring work is actually helping or it does something useful. And of course, refactoring work can be basically anything. If actually refactoring work is something that you can do on basically all of the parts of the software system, of course expecting that there's nothing going on with the module at the same time. Of course, you have to understand that the refactoring work doesn't necessarily have to be the source code of the system. Similarly, as that the code smells aren't necessarily things that are only caused by the source code itself. For example, your coding conventions, your way of design work, or how designs are stored or implemented, or the prototyping work is done, or how your information is collected. Do you have the necessary metrics? Or does your user manual, guides, your tutorials, do they give false information? This is all something that affects the usability and maintainability of the system. If your instructions on how to implement changes for the developers are wrong, of course, then you are going to have problems when someone new comes in and doesn't understand how things should be done. But anyway, consider that the refactoring work might happen anywhere. So you take one part of the software and replace it with something that fills the same role but does it better. And of course, the customer agrees that the area is worth the time and money to refactor is something that's more of a practical issue, but usually the technical problems are more prevalent. So, of course, if you want to do fully agile work, you can also do some refactoring work every time you fix a bug within a system. But this is more, but if we want to keep the fixing things cycle and refactoring cycle separate, that's also somewhat of a strategy, because at least on some organizations I know that the refactoring cycles do not address any of the bugs or any of the feature requests or stuff like that. You need to have very stable build when you do refactoring work, because like mentioned earlier, you need to have a way of comparing that these fixes or changes or refactoring work actually works. If you refactor something, break something down the line, and then it's going to cost more money than it saves. So of course you need to have a way of proving yourself, and for the quality purposes that okay, this is now it works. And of course, if you don't have a stable build, you just don't do refactoring work. It's like if you don't have the testing infrastructure or the test coverage, you should focus on that part. If you don't have something that builds or something that's deliverable, of course that's more pressing issue, because fundamentally all software projects aim to deliver something that works, or they fail. So of course, because refactoring work is somewhat considered redoing a work that has been already once done, but this time better, then it's not worthwhile to start refactoring work when you still have areas that don't work or areas which are problematic. And of course, if you want to do refactoring work, especially on a critical component, you have to be prepared for the possibility that the simplification simply doesn't work. You have to roll back, and then everything you did or the effort you spent on that work is wasted. Or if you leave it as a sort of working set of new bugs, then it basically harms more than it does good on your system. So before we go to the technical, the code smells part, you also need to understand that the earlier slide, which said that you need to define when something is done, is actually a really important thing. So you can, of course, do unnecessary tinkering with your source code. Try to make it a bit better. Try to do some small optimization. Try to do this, try to do that. But it's not necessarily worthwhile to always just do refactoring work, even though the Beck and Fowler say that it's one of the most important things you do during the software development. So we are not trying to make a perfect source code, because changes always happen. That's because the technical systems and the operating systems and the platforms keep changing all the time. But if you don't have, let's say, finish line or objectives, or when something is done or good enough, it just wastes your money. So when you start to do refactoring work, you should probably also set the objectives, what you want to do. Cut the size down by 15%. Cut the performance time by the calculation time by 15%. Do something. Make the application use 5% less battery or whatever you are doing. That's probably going to be something that needs to be set before you start doing refactoring work, so that you know when you have successful solution. And of course, understand that databases probably, or data storages, are probably going to be really painful to refactor, because you have to understand that in most industries you need to be able to access the data for a long time. The backwards compatibility is very important on that area. So some database refactoring can be really difficult and really costly. Similarly, if you have interfaces, if you refactor things like remove unnecessary or unused attributes, those probably are going to be a problem, because if you make changes to how the component is called or how the module or object works, then you need to have a system or infrastructure which explains this new approach everywhere. So perhaps moving some mandatory attributes to additional or selective attributes is still okay, but making the interface completely different than it was is probably also going to cause a problem. So at least have a way of doing, use the approach like, for example, some programming languages use. For example, Python has this deprecated features list, which means that you can more or less use the current state-of-the-art approaches, but you can also import or use the approaches from, let's say, 10-year-old version of the system by introducing or importing the legacy support or deprecation support. And these things don't happen. Because they are unnecessary. These things happen because your project might be your involvement might only be the 1 or 2 years of the project or the software life cycle, but the system might have to live for 20, for even 40 years if we are talking about some database tools or business data management in which, for example, loans, ownership of the house, these sort of things are done in several tens of years time frame. And if you want to deprecate something from the database, it might mean that you have to make changes to the data which has accumulated for several, even tens of years, and might actually mean that it's unavailable at that point onwards. So of course you shouldn't do that unless it's really necessary or really needed change. Similarly with the object interfaces, but that's usually more of an internal problem, because if you just keep making changes to interfaces, you are introducing problems throughout the system. So, of course, these have been more or less already talked about. So, if you have resistance on that the refactoring work isn't necessary, it's usually a couple of combination of couple of things. First of all, you have to understand that people who are not software engineers or software developers might not understand the point of recreating code that has been already done. And even if they do, the fear of breaking current system or current program or current state of the system is really huge. I mean, I have worked with the software organizations which collect all the necessary information, collect all the feedback from the projects and from the people involved, and they fairly well understand what are the problematic areas or what are the missing tool supports and what are the missing areas on which they have really no information, things just happen and so on and so on. But they don't, well, every time they have these reflections or feedback workshops, they more or less decide that they will not do anything because the system still works. And that's not necessarily a good thing in the long run, but a short-term thinking that, okay, our system still works, so the short-term focus is on delivering something that works. They might necessarily not want to invest on a project which might cause them to have a huge problems later in the future. So, going back to the last topic of the lecture. So, what are the code smells that were mentioned a couple of times already in these lectures? So, basically, code smells are design patterns. Design patterns showing that there's something wrong with the source code. Not necessarily, but it's an implication that this design has problems or this design could be enhanced or simplified or is unnecessary system. And of course, the code smells are basically everywhere. They are in production code, in the test code, in the test automation suite. For example, they might also be in the user guidance or your own coding convention guidance or examples or wherever, but usually the code smells are considered to be something that's on the production code or the objects or data objects that the system manages. So there's a book by Fowler on code smells. There's a huge list of these things. These are all design patterns explaining how something is defined on the system. So there's unnecessary comments. There's only classes that have which has only the role of containing data, or middleman classes, or message chains, and so on and so on. Of course, I'm not going to go through these here. You can find the book and find the explanations online, and it's actually probably more worthwhile to check out what these different things are when you are actually doing refactoring work. There's a couple of more of them. So yes, there's several things that you could be looking into, finding problems that probably are going to cause problems later. So starting with the comments. So comments, like mentioned earlier, are usually an indication that there's a problem in this area, or that the developer didn't actually understand what they were doing or had difficulties making the system work. The duplicate code, also talked earlier, there's some ways of how the refactoring work can be done. These are more or less simplified versions from the examples in the book. Or data class. So the class whose only purpose is to hold data, and it has instance variables, getters and setters and stuff like that, which by themselves isn't that bad, but it creates unnecessary entity which can be combined or encapsulated to somewhere else. Or data clumps. Set of variables usually passed together in multiple places, meaning that you might actually want to reconsider what you want to do with them, or should you make a just object that you send from one place to another instead of huge amount of different variables. Or inappropriate intimacy, meaning that you break the visibility rules or privacy rules of the object, meaning that there's probably something wrong with the association between the different objects, and so on and so on. There's large class with too many instances, too much code, too high complexity, so on and so on. So basically these different code smells are more or less something that's fairly understandable. So if, for example, long method, too many statements, loops, variables, lazy code that's not used anywhere, these sort of problems or implementation difficulties, which are more or less understandable from the viewpoint of software developer. You want to reduce the complexity, get rid of all the unnecessary things, because all the unnecessary things which are left in are prone to cause problems later on. So you want to get rid of all the things that you don't necessarily need. Or middleman classes, the class that simply exists to call other classes or doing something like that. There's a couple of ideas on how to deal with the code smell. Of course, some things like the comments obviously are not things that you just delete the comments and now it's good. You more or less have to see why this happens, and if you really want to do something for it. Of course, there's a couple of people from the agile industry saying that you should always get rid of everything that's considered a smelly code, because, like mentioned earlier, it's something that probably going to cause you a trouble. Anyway, the list on different code smells. What are from the maintenance point of view or development point of view, bad things which should be refactored away and which are causing more technical depth than allowing solutions for your software. There's a huge list of them. So the original reference was included on these lecture slides. I highly recommend that you use Google Scholar and go check out the list of different code smells and see what sort of things there are. It's not that they are difficult or complex to explain, it's just that there's like 100 of them, so it's not really worthwhile to go through it here. And of course, on those explanations, they also explain what could be done, what could be considered harmful, and like mentioned earlier, you might not even want to refactor or get rid of all the different types of smelly codes because simply it's not always worthwhile to fix problems that aren't there. Of course, some larger problems you need to fix, but you first need to decide if this is something that's actually going to be a problem. So, as one of the last things I want to remind you is that even though usually the smell is considered to be the source code itself, you also need to consider or sometimes refactor other things like the source code. For example, the test data or the test data set, or how the test data generation is done, how the bad architecture could be fixed, all the bad solutions, for example, even in your development architecture or your test automation suite, or where you are making notation for explaining what things the automated unit tests check on this component include. They are all problematic areas because the code smell doesn't necessarily mean that you have a bad source code or bad programming practices. It just means that this part of the repository or this part of your project is causing maintenance issues or slowing you down or requires way much more attention from your development team than it has any right to demand. So, from this lecture, take home the definitions of technical depth and refactoring work. So, what is technical depth? What is refactoring work, which usually helps dealing with the technical depth? And how can you find the code smells, what they are, and how can you use them to fix your software, or why you at least need to know what they are so you can maintain your source code or software repository when you are doing further development. Okay, that's that. I thank you for being here today, and next week we will be having the lectures like this again, and I'll hopefully be able to tell you more about the guest lecturer and the guest lecture schedule and topic in a week to week, depending on when the person has time to come up with ideas on what he's going to be talking about. Well, it's going to be a software maintenance and software development work. It's not going to be a circus act or archery or anything like that, but I'll be talking about what the actual topic will be in a couple of weeks. Okay, thank you.